Okay.
Okay, so this is joint work with my PhD student, Rolf Morel, at the University of Oxford. So we'll start by just saying, what's this talk about? Well, the main thing is we're going to describe a very, very simple ILP approach. There's only one thing to take away from today's talk, is that we can actually do ILP quite nicely with a very, very simple approach. Basically, the approach has the same functionality as most existing systems, but it offers better performance. So I'm not going to cover any technical details at all. Look at the paper for those. I'll only describe the high-level ideas. So where's the motivation for this work from? Well, it's mainly from the limitations of existing systems. So for instance, recursion is very important, like to learn algorithms, program synthesis, things like that. But quite a lot of the ILP systems struggle to learn recursive programs. Likewise, quite a lot of the newer systems struggle with large domains. For instance, the ILP requires ground facts as a background knowledge. So if the domain is very big, it just doesn't scale well to them. Quite a lot of systems also struggle with large hypothesis spaces. For instance, these three systems like ILASP, they pre-compute every possible rule you could have in a program. Therefore, they just don't really scale to large rules very well. And then finally, some systems require meta rules, which are quite nice if the user knows about them, but if they don't, it means that these systems are quite cumbersome to use. So what we're trying to do is to come up with a new approach which kind of addresses all these limitations. So our approach is really simple. It's called learning from failures, and it's really inspired by Karl Popper's idea of falsification. And it's really has inspiration from Shapiro's work on model inference system, and then also just Tom Mitchell's version of space algorithm. So it's very similar to existing approaches. Essentially, the idea is that we're just going to form a hypothesis. Then we're just going to empirically try to refute it on the data. If the hypothesis fails, or if it's falsified, we determine why, come up with an explanation why. And then we use the explanation to eliminate other hypotheses. And we repeat this. We just keep going round and round. So you can see it as this loop. It's a generate, test, constrain loop. So I'm going to start with an illustrative example. Well, let's suppose we're just trying to learn a program hypothesis which finds the last element of a list. So here we have some positive examples in green, some negatives in red. Laura goes to A, for instance, as a positive. Emma doesn't go to M, because M isn't the last letter. Or we can represent these, just for simplicity, as binary relations. The first argument's the list, second element's the last element. Well, let's suppose we have this hypothesis here, this hypothesis space, which has eight hypotheses. Just to make it clear, we do not pre-compute the hypotheses in our approach. We do not pre-compute the rules or anything like that. It's just for illustrative purposes. What are we trying to do now? Trying to find a solution. Well, our approach just says, well, since we don't know anything else, we're just going to blindly generate the simplest hypothesis we can first. So in this case, we've generated H1, which just says the last element is a head element. We test this on the examples and we say, look, it's not very good because it doesn't entail the positive examples. So what's the explanation here? Well, it's pretty simple, is that just this hypothesis is logically too specific. It doesn't entail enough. So what we do in our approach, we say, well, now we can eliminate H1, but we can also eliminate H2 because all that's doing is adding an extra literal. So it's just making it even more specific. Likewise, we can eliminate H3. So we do that, and now we repeat the process. We say, okay, we've eliminated, falsified some hypotheses. Now let's generate another. So then we generate the next simplest one we can. Test it on the examples. In this case, we find out actually it does correctly generalize the positive one, but it incorrectly generalizes the negative one because it says Emma goes to M. So the explanation here is that this hypothesis is actually too general. It entails too much. So from this, we can eliminate that hypothesis, but we can eliminate any hypothesis that's logically more general. For instance, essentially anything in this case which adds a rule to that existing rule. So we can eliminate H6, H7, and we repeat again. Now we generate H5, we try it on the data. We find that it actually suits the data pretty well, so we cannot falsify it. So we just say that's the best we can do. This doesn't fail, so we'll return that. So that's a high level idea. And it's very similar to existing approaches, as we said. But how do we do it? Actually, how do we make this work efficiently? Well, it's pretty simple. We just formulate the whole thing as a constraint satisfaction problem, where all we're doing in this loop is accumulating constraints to rule out hypotheses. So in particular, we formulate it as an answer set programming problem. There's no particular reason for this. We just found ASP quite easy, but we could formulate it as a SAT problem or as a actual constraint satisfaction problem. But in this case, we use a ASP problem, formulate it as an ASP problem. So what we mean by this is that we come up with a formula or a program, an ASP program, where the models to that program or answer sets represent hypotheses. And all we're doing, we're saying to the ASP solver, find us an answer set which represents a hypothesis. And then as we add constraints as we go through, we eliminate answer sets and therefore eliminate hypotheses. So that's what a generate step does. Look into the paper for more details about this. So when we actually call the ASP solver, it finds us an answer set. We translate that to a definite program or Prolog program, test it on the examples. And we use Prolog because it has some nice features in that, for instance, it can handle very large and infinite domains, which is really handy with numerical data. Complex data structures such as lists and things are trivial. So that's why we use Prolog. And then after that, if we find that the program or the hypothesis doesn't fit the data, then we generate constraints from that. So we actually reason about the program, try to find an explanation for the failure, come up with ASP constraints, add this to our generate program, and then repeat the process. So each time we do a loop, we're eliminating at least one hypothesis, but often we'll eliminate whole classes of them. So what do we mean by these constraints? Well, essentially, it's just hypothesis constraints are constraints on the syntax of hypotheses, and we use theta subsumption to reason about them. The main thing is that the constraints we come up with in the paper, they're all sound. So by that, we mean they don't prune optimal solutions. Look into the paper for more details. So essentially, we put an argument that this system popper is quite powerful, and does it work? Well, the main question we want to know is, can constraints improve learning performance? So this whole loop, is there any point in the constraint stage, or is it actually faster just to quickly enumerate programs? If we can't beat that, then obviously there's a problem with the approach. Now, the second question we're trying to answer is just how does it compare to the other systems? So a slight warning beforehand is that the experiments I'm going to talk about, they're really boring. They're all on contrived data, contrived experiments, purposely designed to essentially test the scalability of the system on various dimensions. Nothing to do with real world data in this paper. So in the first experiment, what we actually wanted to do is just compare the performance of the systems when we vary the size, the rules it's trying to learn, essentially the hypothesis size. So we came up with a very simple contrived example where we're trying to learn the rules of a game where the user has P buttons they can actually choose or select. And we're trying to learn which N buttons need to be pressed to win. So in this case, there's 3 buttons. You can see them on the screen. But we picked this domain because actually we are varying the number of buttons which need to be pressed and the number of buttons available. We can easily control the size of the hypothesis space. So even in this simple example, this hypothesis space is pretty big. So it's quite a nice contrived example. So in this plot, we actually compared the systems. On the x-axis, we say we have the number of buttons which need to be pressed. So what this corresponds to is essentially the size of the rule in the solution we're trying to learn. What this shows is that essentially the systems which, as we said at the start, pre-compute these rules, such as ILASP, they really struggle because obviously there's an exponential number of rules given more buttons, and given more buttons you can press. So they just don't scale to this problem. Something like Metagol also struggles after a few body literals. By contrast, Aleph and our Popper system performs quite well. So actually can learn rules with quite a lot of body literals. This is essentially showing that our approach can learn quite large rules, which is quite a nice feature. The second experiment, again, contrived to test the scalability of this system, is more about trying to compare how these approaches work with the size of the domain. So actually the size of the Herman base, the problem we're trying to learn. So what we did, we came up with a n by n robot problem, sorry, a robot problem where there's an n by n grid. And what the robot's trying to learn is a recursive strategy that essentially just says, keep moving upwards till you cannot move upwards anymore. So the strategy remains fixed. And what we're doing is actually varying the size of the domain, which is the size of the grid. So here on our x-axis, we have the robot world side. On the y-axis, we have learning time. And we can see again that some systems really struggle. So some systems cannot solve this for any size world. But in general, even ILP and Metagol both start to suffer in terms of performance as we increase the size of the world, grid world. By contrast, the Popper system actually performs pretty well regardless of the size of the system. It's a bit technical to get into, but it's because it's not trying to generate a hypothesis and test coverage at the same time, which is, for instance, what Metagol does. So essentially, it's the complexity it has no, size of the domain has no influence on the complexity of the learning system, which is quite a nice feature. Finally, we compared the approach on program synthesis tasks, some tasks here, such as drop the first k elements of a list, find the duplicate element. And the results, not particularly interesting, is just showing that the Popper system can easily outperform the blind enumerative search and Metagol and ILP on these tasks. This is predictive accuracy. But perhaps the more interesting is just the speed. You can actually learn programs such as drop the first k elements in less than a second without any meta rules or any handcrafted bias, which is quite impressive performance. So essentially, we've introduced this approach, learning from failures and Popper, but why should you care? Well, I think one of the main things is just the sheer simplicity of the approach. It doesn't require meta rules or quick recall and mode declarations or anything like that. So the simplicity is one of the main things. Performance actually performs pretty well, at least in these experiments, has good empirical results. Also, it's feature rich. So for instance, trivially learns recursive programs, optimal programs and the size of the program, and large rules with many body literals. And actually more interesting is what we've done since publishing this paper. So actually, since this paper's come out, because of the simplicity of the approach, we've easily now handled noise handling, predicate invention, parallelization, and we can now learn programs with hundreds, even thousands of rules. So it's quite a big advance on the previous approaches. Not everything is great. There are still some problems. For instance, quite a lot of the other systems can learn rules with negation as failure or higher order programs. So we still don't have the same expressivity as some of the systems, which partially explains why we're a little bit faster. We really struggle with constant symbols, especially numerical values, because we blindly generate programs and test them. So if there's lots of numerical values, we essentially have to try them all. So we're working on addressing that. And then finally, we're just trying to make the system faster. So for instance, Rolf, the co-author, he's working on detailed failure explanation and trying to come up with more complete constraints and some more interesting things, just make the system far, far faster. So that's a very quick overview of the approach. You can go download it, improve it. I'll show it's worse than yours. Also, we don't have a poster, so I forgot to do it. But I'll be in that little game room thing to the right of poster 35 if anyone wants to have a talk after this or in the session. And that's it. Thank you very much.